Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 5, Organic Chemistry 2. Today we will continue on chapter 1, Conjugated by Systems and Pericyclic Reactions. In the previous lecture we covered electrocyclic reactions, and today we will cover sigmatropic rearrangements. Sigmatropic rearrangements is a pericyclic reaction in which one sigma bond is formed at the expense of another. In the process, the pi bonds change their location. In this equation below, we have here carbon hydrogen, and this hydrogen will move from carbon 1 to carbon 5 upon heating. Notice that the migration of the hydrogen occurs on the same direction. To understand this, we have to go and use simple frontier molecular orbital analysis and find out that superficial 1,5 sigmatropic rearrangement is thermally allowed. What do you mean by superficial migration? The group moves across the same face. Let's consider the carbon hydrogen sigma bond here as a HOMO. Okay? Will interact with the rest of that ion system here, which has 4 molecular orbitals, psi 1, psi 2, psi 3, where psi 3 is LOMO for the ion. Notice that for the LOMO we have faces blue, and then red, and then blue. We have here sigma, and we have selected, or that happened, it's blue, so the near adjacent carbon will have blue, then red, and then blue. Again, these two faces are the same, right? So when this hydrogen will migrate on the same face, giving us this transition state where the hydrogen moves on the same face to go to the other p orbital to form a new sigma bond, right? And this is a transition state. In case of 1,7 shift, we have here again CH sigma bond as a HOMO. Then we have the tri-ion system, six molecular orbital, psi 1, psi 2, psi 3, psi 4, and psi 4 here will be the tri-ion LOMO, facing here face red, blue, red, blue. Okay, here is our sigma bond red. The nearby or adjacent carbon will be red, then blue, red, and blue. This carbon number 7 has different face in the same direction with the red of the carbon sigma bond, and so it's blue, and the bottom one here is red. So the hydrogen should go down in order to form the bond. We call it intrafacial migration. Okay, the group moves from one face to another. here the hydrogen will leave here, go down to reach the new identical phase to form a bond. That's why here is up hydrogen, and in the product it is down. Up and 3 sigmatropic rearrangements. Two widely used sigmatropic rearrangements in synthetic chemistry are COP and Claisen rearrangements. They are both 3-3. We break here and form bond in here, right? So we give this 1, 2, 3, and we give here 1, 2, 3. We are building a new sigma bond in here on the expense of this one. We break this one. But why the equilibrium for COP rearrangement generally favor the formation of the more substituted alkene? Why this reaction goes this way? Okay? In the starting material, the alkene is mono-substituted. In the product, the alkene is di-substituted. And we have taken in organic chemistry 1 that the more substituted alkenes are more stable than their isomeric mono-substituted ones. In order to construct the transition structure, we have required 2 3-carbon units. These are allele anion, and we will consider this as a HOMO, and the allele cation, and we will consider this as a LOMO. In fact, these are the same orbital, and combining them so that both components can be suprafacially in thermal process. It is reasonable to predict the chair-like transition structure. So when we have here this one, and with the transition state will be building up in here, breaking in here, and moving the double bond to form this one. So this is our transition state. We can consider the transition state as 2 bases, 1 cation and 1 anion. For the allele cation, we have 3 p orbital, so we have 3 molecular orbital. Phase 2, 3 are the same, so that 3 phases are on the same direction. Here we have red, node, and blue, blue, node, red, node, and blue. In the allele cation, we have only 2 electrons, so this is a HOMO. Where is our LOMO? Here is our LOMO, red, node, blue. Now go to the allele anion. Allele anion would be the same molecular orbital, but we have 4 electrons and 2 in the ground, psi1, and psi2 will be our HOMO with 2 electrons. All right? So here again, the same phase, red, node, blue. Come to the allele cation. Here we have red, node, blue, and the other junk, it's allele anion. It will be blue, node, red. As we can see that red with red and blue with blue, so one will break and one will be form will be formed. Both components can react superficially through chair-like transition state, as we can see. Okay, and this is a 2-dimension, and here is clearly the 3-dimension view. It's like chair. Okay, Claisen rearrangement. Once again, why this reaction takes place? Vinyl allyl ether to aldehyde here with one double bond. Okay, the equilibrium greatly favor the product because of the C double bond O bond, which is thermodynamically more stable, lower in energy than the C double bond C. So this compound is more stable than this one, lower in energy, right? That's why the reaction will go this way. Claisen rearrangement is also observed in allyl ether, like this one. Okay, transition state. Okay, to form double bond O and ortho allyl. You say, okay, but here is stable because it's aromatic. Yeah, this one also, upon tautomerization, this hydrogen here, upon tautomerization, losing 2 electrons, and the double bond will be single bond, and the oxygen will go and catch the hydrogen to form ortho allyl phenol, which is aromatic, right? That's why it's driving force this way. For each of the following reaction, use brackets and 2 numbers to identify the type of sigmatropic rearrangement taking place. In this one, we are breaking here the carbon-oxygen bond, right? And forming a bond in here. 1, 2, 3, 1, 2, 3. This is a 3 sigmatropic rearrangement. What about this one? We are breaking in here. Here is 1, right? So 1, 2, 3, 4, 5. Moving from hydrogen from 1 to 5. This is 1,5 sigmatropic rearrangement. Consider the structure of cis 1,2-divinyl cyclopropane. This compound is stable at low temperature, but rearranges at room temperature to produce 1,4-cyclohexadiene. Draw a mechanism for this transformation. Using brackets and numbers, identify the type of sigmatropic rearrangement taking place in this case. This reaction proceeds to completion, which means that the concentration of the reactant is insignificant when the equilibrium has been established. Explain why this reaction proceeds to completion. Well, taking this compound under thermal condition, we will break in here electrons, move in the transition state this way, breaking this one, forming double bond, and forming cyclohepta 1,4-ene. The new diene is 7-member ring, right? So the cutting in here, 1, 2, 3, 1, 2, 3, this is 3, 3 sigmatropic. And since we are breaking the cyclopropane, the tricyclic, cyclopropane to cyclohepta, which is more stable, that is a driving force because of the ring strain of the cyclopropane ring. Okay, that is a driving force for the reaction to take place. Do you know why vitamin D is commonly called sunshine vitamin? This is the structure of the vitamin D. It's mixture of D2 and D3. D2 different R groups. The D2 has alkene, but the vitamin D3 is saturated alkyl group. So why we call this sunshine vitamin? Although most food does not contain substantial amount of vitamin D already, some food sources do contain the precursors that the body needs in order to synthesize vitamin D. Resveratrol is present in many vegetables, and 7-dehydrocholesterol is present in fish and dairy products. Well, what will happen in sunshine? When we have this molecule in sunshine, electrocyclic reaction, ring opening will take place to form these compounds. Again, R here, and for this one R is here. So these compounds, remember that we have here CH3, right? So we have here CH2H, this H. What will happen to this? Another transition state will take place and migrate this hydrogen from here to this. Here is 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. So it is 1,7 sigmatropic rearrangement to furnish vitamin D, D2 and D3. Okay, first electrocyclic ring opening, followed by 1,7 sigmatropic rearrangement. See you next lecture.